Yes, so it has started, right? Okay. Okay, it has started. So, welcome to lecture number 11 of physics optional for UPSC CSE. Okay, paper 2 is going on. Okay, and uh, Pranav sir has fallen ill, so I am taking the classes. Okay, some students say that we can't believe that you are twins because whatever you speak seems very similar. But the thing is, it's a reality that we are twins. Okay, so if you want the proof, then I can send you the photo also, both of us sitting together. Okay, if you want the proof. Okay, so I am taking the classes. So let me write over here. We will start from basically wave function. Okay, wave function psi. If you observe minutely na, if you observe minutely, then there are some differences between us, between our language. Okay, there are mild differences between our language if you observe minutely. Okay, so and yes, some of the students are asking doubts in the form of comments. So I would say that beta, in the form of comments, if you are asking doubts. Okay, suppose if you are asking doubts in the form of comments, then the thing is that there are about 25 comments each day. There are about 25 comments each day, and it's very difficult to answer those comments. Okay, sometimes the comments just sometimes even I am not even notified that comments have come. Some of the comments are even missed. Okay, so please, it's a request that if you have any serious doubt. Okay, if you have any serious doubt now, then just WhatsApp the doubt. Okay, just WhatsApp the doubt on 724 918 7038. Okay, just WhatsApp your doubt over here. Okay, don't worry. I will reply to it until Pranav sir recovers from his illness. He has actually got dengue. Okay, so until he is well, I am his twin brother, that is me. I am going to reply to your messages, all your doubts. Okay, so this is the thing. So about wave function, what are we going to learn? Okay, we are going to learn its physical interpretation. Okay, about wave function, what are we going to learn? We are going to learn its physical interpretation. Okay, physical interpretation. We are going to learn its physical interpretation, normalization. Okay, orthogonality. In this lecture, we are going to discuss all these things, and criteria for a valid wave function. This we are going to learn in the next class. Criteria for a valid wave function we are going to learn in the, up to here we are going to do in this class. Okay, so agenda of the next class is this. Agenda of next class. Okay, criteria for valid wave function. Okay, okay, so this is the thing. We are going to this is this class topic. Okay, present topic. So concepts are as follows. Okay, keep on writing in the notebook along with me. Capital psi r comma t, that is time dependent wave function, which is denoted by capital psi. Okay, gives nearly complete information. Okay, gives nearly complete information about the state of a physical system. at a particular time at a particular time in accordance with the in in accordance with the rules of quantum mechanics. Okay. So capital psi of r comma t means time dependent wave function. Okay. So it gives nearly complete information about the state of a physical system. Okay. A physical system means a particle or anything like that. Okay. So physical system simply means that it may be a particle or anything like that. So this psi of capital psi r comma t gives nearly complete information about the state of a physical system. Okay, nearly complete information. Okay, it gives nearly complete information. Why nearly complete information? Because you know this very well that wave function Schrodinger's wave function is not valid for relativistic motion. Okay, this is wave function psi is solution of, it is solution of basically Schrodinger wave equation, right? Psi of r comma t is a solution of Schrodinger wave equation, and as it is a solution of Schrodinger wave equation, so it is valid only in case of non-relativistic motion, and spin is not taken into account. Okay, so relativistic motion and spin taken into account, it is not in your syllabus of UPSC. Okay, so let me write over here. Okay, psi of r comma t, psi of r comma t is the solution of the Schrodinger wave equation. Which type of Schrodinger wave equation? Time dependent one. Okay, solution of Schrodinger time dependent wave equation. Okay, so this is the solution of it. Okay, and this does not take into account, this doesn't take into account this doesn't take into account the, okay, this doesn't take into account the spin of the particle, spin of the particle, and relativistic motion. Okay, so Dirac gave Schrodinger wave equation for relativistic motion and with spin taken into account. Okay, so Dirac gave Schrodinger wave equation for relativistic motion and with spin taken into account. Okay, and this Dirac equation, this is called as basically Dirac equation, not a part of UPSC syllabus, not a part of UPSC syllabus. Okay, so this is a part of this is a part of basically your MSc physics. Okay, MSc physics, in it this is there. Okay, in MSc physics this is there. Okay, so psi of r comma t gives nearly complete information about the state of a physical system. Nearly complete because spin and relativistic variation of mass, etc., those are not taken into account. So that's why nearly complete information about the state of a physical system at a particular time. Okay, at a particular time. Okay, in accordance with the rules of quantum mechanics. At a particular time. Why at a particular time? because time term has also come in it. Okay, so that's why at a particular time. Okay, in accordance with all the rules of quantum mechanics, right? Now this psi of r comma t, okay, this capital psi of r comma t is your known as state function. Okay, state function. This is known as basically your state function. Okay, and the why state function, because it denotes the state of a system. Okay, not a system, particle. It denotes the state of a system. Okay, it denotes the state of a system. Okay, so that's why it is known as state function. Okay, and it is a complex quantity. Okay, psi of r comma t is a complex quantity. Okay, so let me write over here. In general, it is complex quantity. Okay, and thus consist of two parts. Okay, it is a complex quantity, so it will consist of two parts. You might have learnt in the complex number at the time of JE, at the time of IIT JE, you must have learnt in complex numbers that every complex number has some amplitude and phase associated with it. Okay, so in general, it is complex quantity and thus consists of two parts. Okay, and thus consists of two parts. Okay, thus consists of two parts. Those two parts are amplitude and phase. Okay, so those two parts are amplitude and phase. Okay, so psi r comma t, we can denote it like this, that it will be basically your psi of 0. I have already told the proof of this in the previous classes. Okay, in the previous classes this thing has been proved in the form of a 2009 year pyq. Year 2009 pyq was there, and in its form this thing has already been proved to you. Okay, so this is basically your constant. Okay, this is basically your amplitude, and what is this? This is basically your phase. Okay, so I had already told you in the proof that this is basically arbitrary constant. Okay, arbitrary constant. So as that is an arbitrary constant, so we can take its value to be equal to 1. Okay, so we are taking for our convenience its value equal to 1. So your psi of r comma t, capital psi r comma t, it turns into psi of r. Okay, e to the power minus I e t over h cut. Okay, this is the form in which it turns. Okay, so now we will move on towards its basic properties. Okay, basic properties of this wave function psi, basic properties of this. Okay, basic properties. So it can interfere with itself. You know this very well from the double slit experiment. What happens in the double slit experiment? In the double slit experiment, electrons get diffracted. Okay, and interference patterns are formed on the screen. Okay, in double slit experiment. So basically in double slit experiment, what happens is that this wave function psi r comma t interferes with itself. Okay, this interferes with itself. So this basically explains this property. This property explains the phenomena I hope you are aware of double slit experiment. Okay, explains the phenomenon of electron diffraction. Of electron diffraction. Okay. Now this is the first property. Okay. Now the second property is, I told you na, it basically explains the phenomena of electron diffraction. Double slit experiment is a great example of it. Okay, double slit experiment is a great example of it, where the wave function psi add on superimposition takes place of the wave function psi, and after superimposition some new wave function is obtained, and that causes interference pattern to be obtained on the screen, scintillation screen. Okay, so you already know that thing. So it describes the behavior of single particle. Okay, it describes, second property is, it describes the behavior of a single particle. The behavior of a single particle, and not the statistical distribution. And not the statistical distribution of a number of such particles. Okay, so it describes basically the behavior of a single particle and not the statistical distribution of a number of such particles. What do you mean by statistical distribution? Statistical distribution simply means that it is either Bose, okay, Einstein statistics, which is followed by bosons, and number two is Fermi Dirac statistics. Okay, Fermi Dirac statistics. Okay, so these two things. Okay, so this so your wave function psi does not go into these things. Your wave function psi does not go into these things, that whether it is Bose-Einstein statistics or whether it is Fermi Dirac statistics. Your wave function psi does not go into all these things. Okay, it only tells about the individual particle. Okay, so it describes only an individual particle, and not an ensemble of such particles. Okay, so your Schrodinger wave equation describes the individual particle and not a ensemble of such particle. Your wave function is also like that only. Okay, what do you mean by ensemble of such particles? Means many particles are there. Many particles means just group of particles. Okay, so it does not describe your wave function psi of r comma t, capital psi of r comma t does not describe the ensemble of a particle, and neither does it describe whether if Bose-Einstein statistics holds, then what will be the Schrodinger wave equation or what will be the wave function. It does not tell. It does not tell if Fermi Dirac statistics holds, then what will be the wave function. Okay, what will be the Schrodinger wave equation. It does not tell. Okay. Okay. So the third, it is large in magnitude. It is large in magnitude, where the particle is likely to be located, where the particle is likely to be located. Okay, it is large in the region where the particle is likely to be located. Okay, uh, and small elsewhere. Okay, and small elsewhere. Small elsewhere means, suppose the particle, there is a discharge tube. Suppose this is your discharge tube, and there is 100% probability that the electron will be found inside the discharge tube. It very almost nil probability is that it will be found outside discharge tube. Okay, the probability of finding of electron outside the discharge tube is almost nil. Okay, but inside the discharge tube it is 100% probability of finding the electron. So so it is large in magnitude. Now when we take the magnitude, when we take the magnitude mod of this psi of r comma t, when we take its modulus, okay, it is a complex number, right? It is a complex number, so when we take its modulus, so it comes out to be a real number. And that modulus basically indicates that uh, what will be the probability at a particular point. Okay, that modulus means magnitude. Okay, we when we take it, so it basically denotes your region where the electron will be located. When electron the region where probability of finding electron is high. Okay, the region where probability of finding electron is high, at that place psi r comma t, its magnitude will be large. And the region where it will be, the probability of finding electron will be less, that magnitude is going to be less. Okay, so now basically according to Max Born. Okay, according to Max Born, Max Born's probabilistic interpretation. Okay, your psi of r comma t. Okay, psi of r comma t, when we take its square. Okay, when we take its the square of its magnitude, I mean. Okay, what does this mean? Square of magnitude. Okay, square of magnitude, square of magnitude of wave function. Okay, so when we take the square of magnitude of the wave function, basically it denotes probability. Okay, it denotes probability of finding the electron. Okay, probability, the read this as probability. Okay, so this denotes probability, and according to Max Planck, and by the definition of complex numbers, when we multiply complex conjugate r comma t with its real value. Okay, with its real value, with it is equal to your modulus square. Okay, it is equal to your modulus square. Okay, so let us take a real life example. Suppose this is a plus ib. Okay, suppose psi r comma t. Okay, suppose, let us suppose that psi r comma t is equal to a plus ib. Okay, hypothetical. Okay, not real. Hypothetically. Hypothetical. Okay, so basically when I take its mod. Okay, what will you, mod means magnitude. Okay, so its magnitude when I take, so it will be clearly a square plus b square, right? Okay, so let me see over here. Okay, magnitude, no, it will be a square minus b square. Okay, okay. No, no, a square plus b square only. Okay, a square plus b square only. So it will be a square plus b square, and when I take its square, it will be a square minus b square. Now this can be represented in the form of psi star multiplied by psi. Okay, so what is psi star? Complex conjugate. So a minus ib, okay, multiplied by a plus ib. Okay, so when I multiply these two, I get a square minus b square. Okay, I get a square minus b square. So your thing will turn again to be a square plus b square, because this iota square will become minus 1. Iota square will become minus 1, and minus into minus will become plus. So you are see, you are getting the same result. Watch what Max Planck told. Okay, not Max Planck, sorry, Max Born. Okay, what Max Born told, this equal to this he told, right? So see, you are getting the same thing, right? Okay, so you are getting the same thing. So you got a square plus b square in both the cases. Okay, so this is the thing. Hopefully you got the thing. Okay, now psi r comma t square, okay, is equal to psi star, okay, r comma t. This we already proved now, right now. Okay, we proved right now, right? You can take any number a plus ib and you apply your JE time maths. Okay, so you will eventually understand that thing. Okay, now this is the thing, in the form of 2009 problem we learnt this thing. Okay, that what is the relation between time dependent wave function and time independent wave function. We learned this in the form of 2009 PYQ. Now this all these are in multiplication, so this multiplied by this will be this plus this will happen, because law of indices will apply, and according to law of indices, when we add the power, e to the power 0 will be obtained. So e to the power 0 will be clearly 1. Okay, so I will get it to be equal to, okay, psi r, right? So this is the thing which I got, and this thing is eventually equal to your psi r modulus square. Okay, and this is equal to your probability density. Probability density. Probability density means per unit volume how much is the probability. Probability per unit volume. Probability density means probability per unit volume. That means probability at a single point, at a small point, at a differential volume element. Okay, that is what is meant by probability density. Okay, so from here you can clearly see this thing, that psi of r comma t whole square, okay, equal to psi r, okay, square. It is the probability. Okay, probability of finding of particle in unit volume. I told you right now, in unit volume of the space at a particular place at given time. At the particular volume of, say, at a particular place at a given time. Okay, at a given time. Okay, so let us understand the meaning of this. This denotes the probability of finding a particle in unit volume of the space. Okay, it denotes basically probability. Okay, probability of finding particle, probability of finding of particle in unit volume of the space. Okay, unit volume of the space means, suppose this is the space I have. Suppose this is the space I have. Suppose this is 3D volume. So in unit volume of this space, unit volume, suppose there is a differential volume element like this. So in unit volume of the space, I will find the probability. So this unit volume of the space is at a particular place. Okay, this is at a particular place. Okay, and as it is time dependent one, so basically it is at a particular time. Okay, so at a particular time. Now the thing is that this term and this term, okay, these two terms, you can clearly observe this thing that probability density has come out to be independent of time. Okay, so probability density comes out to be independent of probability density comes out to be independent of time. You can clearly see from here. And one more thing, I didn't tell you the meaning of conjugate of a complex number. So conjugate of a complex number simply means, what is the meaning of conjugate of a complex number? Suppose this is my complex number a plus ib. Okay, suppose hypothetical, such numbers are not actually wave functions, but let us assume in a hypothetical manner, then what will be its conjugate? Okay, so in order to find the conjugate, just replace I by minus I, just replace I by minus I, and that's it, your conjugate will be found out. Okay, and one more thing is there, that yes, this is the thing. And over here this was this thing was there. Okay, this thing was there, and you were finding basically its conjugate. So amplitude conjugate. Okay, amplitude conjugate, and basically phase conjugate. So phase conjugate, I will be replaced by minus I in the conjugate. Okay, both these are complex conjugates of each other. So hopefully you got that why it is plus I over here and why it is minus I over here. Hopefully you got that. Okay, and over here one thing I have forgotten, that it should be basically this symbol must be there. Okay, so I forgot that symbol, so just put it over there. Okay, now so probability of finding, now we will find the probability in a unit volume. Okay, in a unit volume we are going to find out. So let us suppose that these three axes are there. Okay, these three axes are there. Suppose x, y and z axes are over there. Okay, let us suppose x, y and z axes are there. So this is your x axis, this is your y axis, and this is your z axis, suppose. Okay, and suppose at a position vector r, suppose there is a volume element, small volume element. Okay, volume element is there, which is of the cuboid shape. Okay, it is of cuboid shape at a position vector r. Let us suppose it is d tau. Okay, so probability of finding particle in elementary volume d tau. Okay, let me write over here. So probability of finding of particle in elementary volume d tau, okay, is given as, how will it be given? Just apply your unitary method. Okay, just apply your unitary method. You know this very well, that this is the probability density per unit volume. Okay, what is this? Probability density per unit volume. Now I have to find the probability density for this volume. Okay, I have to find the probability density for this differential volume. So in order to find the probability density for the differential volume, what will I do? I will basically multiply this expression, okay, by applying unitary method. I will do, okay. This is the probability density per unit volume. So if I multiply it by volume, then I get the probability density over that differential volume, okay. So dp r comma t. Now how has this unitary method come? You know that if one chocolate costs 2 rupees, then two chocolates will cost how much? 2 into 2, that is 4 rupees, right? So suppose this is the cost of one chocolate. This is the cost of one chocolate, okay. So how much will d tau chocolate cost you? So d tau chocolate will cost you this much. D tau chocolate will cost you this much, okay. So that is called as unitary method, okay. So this is the thing. And the dp r comma t, okay. Now we know this very well that we have taken a cuboidal type of elementary volume, right? we have taken we have taken basically cuboidal type of elementary volume, okay. So cuboidal type of elementary volume we have taken. So clearly this thing will eventually, okay, give you dx dy dz, okay. Dx into dy into dz you will get, because it is a cuboidal type of volume, right? Having length equal to dx, breadth equal to dy, and height equal to dz, okay. So that such a cuboidal differential volume was there. And basically in order to find the volume of a cuboid is given by lbh. So all these three things will be multiplied, okay. All these three things will be multiplied. So that's why dx dy dz has come over here. This is dx dy dz, okay. Read it like that. Now we have to find the probability of finding the particle in a finite volume tau, okay. It was a differential volume. So in the differential volume we clearly got this. In the differential volume we clearly got this, right? In the differential volume we got this. This is what we got in the differential volume. This is what we got in the differential volume. Now we have to find, so the probability of finding of the particle in a finite volume tau is given as. So we have to find the this probability density in a finite volume. Now you always know this thing that whenever we transit from a differential element to a finite element, whenever we transit from a differential element to a finite element, we integrate. You know this very well, right? So we will basically do the integration over here now. So after we do the integration, we will obtain a result like this, okay. So it will be volume integral. It will be volume integral, okay. Volume integral. And this is your unit volume one, okay. Dx dy dz, okay. Square dx dy dz, okay. So this is the thing, probability of finding the particle in entire volume, okay, entire volume, because this is volume integral basically. You might have learnt your volume integral if you had maths as your subject in BSc. Then you might have learnt this volume integral also, okay. So this is the thing, or in engineering, that they also teach the same, okay. Now this thing is very one thing is very remarkable over here, that if all space is taken, okay, if all space is taken, all space means all space is taken means whole universe is taken. If whole universe is taken into account, this the volume integral will what will the limits of this volume integral, you know this very well, that for a whole space, okay, for whole space this volume integral will turn into all space, okay, all space will be written like this, and it will turn into basically your same thing will be written, okay, dx dy dz, right, is equal to 1, okay. So now we can write this like this, that whole space means whole universe, and universe is very big, okay, whole space means whole universe, and universe is very big, it is its limit are in light years, okay. So instead of putting the limits of this volume in light years, I am putting infinity because it will be almost infinity only, and the universe is expanding also, so I have to put infinity because there is no upper limit to it, okay. So dx dy dz, which is equal to 1, okay. Why it will be equal to 1, you know this very well, that in the whole universe there is 100% probability of finding the particle, because where will the particle go, the particle can be anywhere in this universe, outside this universe the particle cannot go, right. So as the particle cannot go outside this universe, the particle is bound to find in the universe, bound to be found in the universe. So obviously if I integrate from minus infinity to infinity in all the three dimension, it will cover entire universe, and if it converts and if it covers entire universe, then obviously you know this very well, that 100% probability of finding corresponds to the number 1, okay, 100% probability corresponds to the number 1. So this integral will eventually be equal to 1, okay. So this integration will eventually be equal to 1. Now some students get confused over here. Sometimes what happens is that this all space, remember this thing, that all space does not imply entire universe all time, okay. Let me write over here, or entire space uh, does not necessarily imply minus infinity to plus infinity, does not necessarily imply minus infinity to plus infinity limits. Why? Why? Because suppose there is a discharge tube. Suppose there is a discharge tube, okay, and in the inside this discharge tube, the probability of finding the electron is 100%, okay. So and outside this discharge tube, in the entire region outside this discharge tube, the entire universe outside this discharge tube, it has 0% probability of finding the electron. Suppose, then why will we integrate from minus infinity to plus infinity? Why will we integrate like that? Because the probability of finding the electron outside this discharge tube is already 0. So we will simply integrate, we will simply integrate the dimensions of this discharge tube only, because the for this electron which is bound to bound to be found in the discharge tube, for such an electron the entire universe is that discharge tube only. So why to go minus infinity and plus infinity? Instead, put the dimensions of the discharge tube, right? Instead, put the dimensions of the discharge tube. Why will you go to the entire universe if it is sure shot that the probability of finding the electron is 100% inside the discharge tube? Then why will you roam the entire universe? Why will you go to the entire universe? So minus infinity to infinity, all space or entire universe does not necessarily imply that minus infinity to infinity will be the limit. Does not necessarily imply. In some of the situations where the probability of finding electron is 100% within a specific region, so at that condition, this minus infinity to plus infinity will not hold. Instead, it will hold that your probability of finding the electron is 100% within that volume. So within that volume, whatever are the dimensions of that volume, you will put those limits instead of putting minus infinity and plus infinity. Okay. But if nothing is given in the problem, then simply you have to put minus infinity and plus infinity. Because in that case, if nothing is given in the problem, like the electron will be surely found in the discharge tube, like that such statement are not given in the exam, then you have to consider minus infinity to plus infinity in that case. Okay. So basically we got this thing. Okay, we got this thing, and this is what is called as normalization condition. Okay, this is what is called as normalization condition. This is what is called as normalization condition. Okay. Now let me give you an example if you haven't understood the concept clearly. Okay. If I say there is suppose your home. Okay, there is your home, there is your city, there is your city, there is India. Okay, and this is Earth. This is suppose Earth. This is suppose Earth, and this is suppose entire universe. Okay, this is universe. Then tell me what will be the probability of don't you think that your probability of being found increases with increase in the subset? In the probability of you being found in the home, probability of you being found in the home is less than the probability of you being found in the city, because you can roam anywhere in the city. It is not a guarantee that you will be inside the home only, right? You can be anywhere in your city. Okay, you can be in your home also or in your city also. So as your city includes your home, your probability of being found in the city is more as compared to your probability of being found at the home. Okay, but what about your probability of being found in India? Obviously, it is more than the probability of you being found in your city. Because suppose if you live in Delhi, yeah, and you go to some city, okay. So if you go to certain city, another city of India, other than Delhi, then obviously your probability of being found in India is more, because you can be anywhere in India. But what if I say Earth? Then your probability becomes almost 100% that you will be found anywhere on the Earth, because you can go to foreign also. So your probability increases of being found. Your probability of being found increases because the size of the space is increasing. Because the size of the space is increasing. Home is smaller, city is larger, India is even bigger, yeah, yeah, Earth is even bigger than India. And okay, and for some astronaut, the probability of being found outside the Earth is also not zero. Okay, because some astronaut may go to moon also. Okay, like Neil Armstrong. So probability of Neil Armstrong being found on Earth is not 100%. Probability of Neil Armstrong being found is 100% in the universe, but not on the Earth. Okay, so for such astronaut type of people, we will integrate for entire universe. So integration will hold. So this integration limits will hold minus infinity to plus infinity for astronauts. Okay, for astronauts, entire universe is the limit. For people like us, the whole entire space is the Earth. For people like us, entire space is the Earth. For astronauts, entire space is the universe. For a person not going to foreign does not for a person not having visa, a person not having visa and passport, the probability of being found in India will be 100%. A person who is very much suppose someone has done a crime and he is on bail. Suppose someone has done a crime and he is on bail, then his probability of being found in the city is 100%. So we will integrate for the limits within the city only, not India. Okay, because his probability of being found in the city is 100% because he is on bail. He has been released on bail. Okay, and suppose there is corona lockdown. Suppose there is corona lockdown, then your probability of being found at the home is 100%. Okay, so depending on the situation, depending on the situation we will basically change this integration limits. Okay, so that's why I have told that all universe or entire space does not necessarily imply that minus infinity to plus infinity limits. Okay, so it does not necessarily imply minus infinity to plus infinity limits. Okay, so keep this in mind. Okay, so the now let us write over here. Okay, this is your condition, right? This is the condition which you got. Psi r comma t square. Okay, dx dy dz. Okay, is equal to 1. Okay, so a wave function satisfying the equation. Okay, the equation on the previous slide. Okay, is said to be is said to be normalized. Okay, so a wave function satisfying this condition, that when we take the integration over entire space it is going to be equal to 1. So a wave function satisfying this condition is said to be basically normalized. Okay, and it is quite sure that the solution of Schrodinger wave equation, whenever we find the solution of Schrodinger wave equation and we obtain the value of psi, whenever we obtain the solution of Schrodinger wave equation and we obtain the value of psi, definitely it is going to be normalized. Okay, definitely it is going to be normalized, because definitely it is going to be normalized because the probability of finding the electron or any other particle over the entire space will always be equal to 1. So a valid wave function, for a wave function to be valid, it must be normalized always. Okay, for a wave function to be valid it must be normalized always. They keep this in mind. Okay, so this is the thing. Thank you very much. जय हिंद जय भारत. अपना ख्याल रखें और देखते रहे हमारे इस चैनल को. ओके.